Guys, I have no idea where my little camera went. I think you can see my paper on this document, but I think I disappeared. So, okay, well, I am not here today, and so I thought it best if I make a quick video to cover the content that we need to look at right now on types of chemical reactions. So the other day we did balancing of equations, and you guys did a great job balancing your equations. Okay. So now we need to look at the types of reactions that we have. And you've already looked at 4 of these in our POGL: synthesis, decomposition, single displacement, or replacement. Sometimes those words get switched around, and double displacement or double replacement. Okay, so we've done these 4 in our POGL. The newest one that we're going to add in is combustion. And you've actually balanced combustion reactions. We just haven't called them that yet. So let's review really quick what they are. And then we can go through those homework sheets and go back and try and identify some of these types of reactions. So the first off is synthesis. Also, sometimes it was just a direct combination. In other words, we're taking multiple things, we're putting them together, we're making one big product. So I think that our big takeaway when we look at a synthesis, kind of like our big flashing sign, is one product. Okay, it is the easiest one to recognize, I think. When we take 2 or more substances and we combine them to form this one product, okay? And this reaction is going to give off heat. So kind of like, when you create water, what we see in our space shuttles are actually hydrogen gas and oxygen gas coming together to make water. But because they're liquid versions of the substances, there's such an extreme amount of heat that's produced that it actually allows the rocket, the booster, to push the space shuttle up off the ground. Here we had aluminum and oxygen come together to make aluminum oxide. So when we build bonds, it is an exothermic reaction. We give off heat. Because think about it, if we break bonds, we need energy to break the bond. So in this case, we're not breaking the bond, we're building the bond. So here, thereby, we are letting go of heat. Okay. So it can be as simple as A plus B makes AB, but it can also be a little more complex. Like, it doesn't just have to be 2 things coming together. It could be A plus B plus C, or A plus B plus C plus D. But again, one product. Okay. So that's your big takeaway from synthesis, is one product. Now, on the flip side, we've got decomposition. So this is when a substance breaks down into 2 or more simpler substances. Okay, so because this is the reverse, we're going to have one reactant. One reactant, okay? So it is the reverse of a synthesis. And where the synthesis gives off energy, the decomposition is going to require energy. So think about, like, something's decomposing in the woods. Well, if it's in the wintertime and it's really cold, that doesn't really happen very quickly. And whether you're thinking of it from my forensic science class of a body, or you're thinking of a small scary animal, or even just leaves and plants and plant life, when there's colder weather and dark areas where they don't get a whole lot of sunlight, they don't get a lot of heat, it's a much slower process, right? But when they can have more energy, then that decomposition is going to happen quicker. So they need energy to make the decomposition happen. And so that means it's going to be an endothermic reaction. We got to put energy into it to break these bonds. So it could be as simple as just AB breaking down into the 2 components of A and B. So here's the aluminum oxide breaking into aluminum and oxygen. Hey, by the way, aluminum's Al, but oxygen's O2. Why is aluminum allowed to be alone, but oxygen not? Well, hopefully you remembered oxygen is a diatomic, and it can't just be a single O. It has to be O2. Part of that Brinkelhoff. Okay. But you can also have something more complex, like we talked about up here, where it could be ABC or ABCD breaking into multiple pieces. And again, if anybody is alone, double check if they belong to Brinkelhoff. And if they do, you got to put them in diatomic form. Okay? So that's synthesis and decomposition, two of the very easy ones, and they are the reverse of each other. Okay? Now, the new one that we haven't talked about yet is combustion. So combustion is pretty much just the burning of something, right? When we think of burning a fuel, burning a gasoline, burning an alcohol, burning a gas, that's combustion. Okay, so it occurs when a substance reacts with oxygen and it produces energy in the form of heat or light. We produce one or more products that contain the elements in the reactants. So in other words, we're using these reactants and we're creating products with it. And combustion reactions always involve molecular oxygen. So it's just a fancy way of saying, hey, they require O2, oxygen. Okay. So what we're going to see is we're going to take some kind of fuel. Okay. Usually a hydrocarbon, which just means a molecule that has hydrogen and carbon in it. But it can also have oxygen in it. In this case, this is an alcohol. And so this is a simple alcohol, methanol, and it's got carbon and hydrogen and one oxygen, okay? But you're going to see when we have combustion reactions that this fuel may change, and it can be, just carbon and hydrogen or carbon, hydrogen, and oxygen. But this fuel could get really big, it could be small, but then the rest of the items are going to be identical. So they're all going to require oxygen to burn. They're all going to produce carbon dioxide, and they're going to produce water, and they're going to give us a lot of heat. That's the whole reason we're burning them. Okay. So, and if you don't have that oxygen, then the flame, that thing that's burning, is eventually going to go out. Okay. So we're going to see where this is going to change to different items, different types of molecules with carbon and hydrogen or carbon and hydrogen and oxygen. But these three will stay the same: oxygen, carbon dioxide, and water. Okay. So this is kind of the thing that you're searching for when you try to spot a combustion reaction. Is there oxygen in the reactant, and is there carbon dioxide and water in the product? Okay. Okay, so we're moving on to single replacement. Okay. Now, in a single replacement, one element and a compound are reacting, and then the element is going to replace another element in the compound. So really, we're looking for one element plus a compound, and it's going to produce one element plus a compound. Okay, so, but you got to keep in mind that like replaces like. If your single element is a positive ion, would be a positive ion, then it's going to replace the positive ion that's in the compound. And if it's a negative ion, it's going to be looking for the negative ion in the compound. Like is going to replace like. So the new compound is made using the ion's charges, the crisscross method, and one element remains. Check if it's a Brinkelhoff, and then it should be in diatomic form. Okay? So, in other words, we're looking at A plus BC. Okay? A single element plus a compound is going to produce a single element and a compound. But you got to check and see what A is. Get out your red periodic tables. Flip them over to the side that's marked periodic table of ions, and look up what kind of element A is. Is it on the metal side? Is it going to take a positive charge? Okay. Or is it on the non-metal side? Is it going to take a negative ion charge? So in this case, this first example, A is going to take a positive charge. Okay. So we're going to think of A as having a positive charge. So if that's the case, A is going to replace B in the compound. Because remember, when we write a compound, we always write the positive first and we write the negative second. So if A has got a positive charge, it's going to replace the front end of the compound. Okay. So we see here that aluminum is going to replace silver. Okay. And I always tell kids, when you see these, get out that periodic table and start looking them up. Aluminum, when I look it up, is a +3. Silver, Ag, is a +1. And sulfur is a -2. So then if I see these charges up here, then I know like, hey, Al is positive. It's going to kick the other positive out of the compound, which is going to be Ag, and take its place. And then over here, I can see what that new compound is going to be, because it's going to be Al, which is a +3, and now it's going to be with S, which is a -2. And I can see where my formula is coming from, because crisscross applesauce, I need 2 aluminums for every 3 sulfurs, and that's how they got Al2S3. Now, Ag got kicked to the curb, right? Aluminum walked up to this compound, said, Ag, you take a hike, man. I'm going to take your boyfriend. And aluminum came in and bonded with S. Okay, so aluminum's now with sulfur, Ag's out in the cold. Now, double check, can Ag be alone? Yes, because it's not a diatomic, so it can just be Ag. But if it belonged to Brinkelhoff, you would have to make it as a 2, okay? Now, down in the bottom example, though, A is going to act as a nonmetal. So if you got to this single element and it was a negative, if A was a negative ion, then remember your B is going to, the front of the compound is always positive, the back of the compound is always negative. So in this case, A would be trying to replace C, okay, which is the other negative. So in this example here, F is going to take the place of a nonmetal, right? So we think of F as being a -1 charge. And when we look up Na is a plus and Cl is a minus. So fluorine being a negative is going to try and kick chlorine out and send them to the curb, okay? So fluorine is going to kick chlorine out. So here's chlorine all by themselves. But why is chlorine a Cl2? Well, that's because it's diatomic. It's a Brinkelhoff. So it's got to be in diatomic form. And then fluorine's going to bond with Na. And again, use your charges to help figure out your new compound. Na is a plus, F is a negative, so therefore you're going to get NaF as your compound. So in a single replacement, again, it's one element and a compound making a new element on its own that came out of this compound. And then a new compound, okay? Now, there's one more rule to this. When you have a single replacement, this can only happen if the single element that's going to kick the other element out is more active or stronger. Now, what that means is it's a bit of a totem pole of, or hierarchy of who can kick who out. Okay, you have to be more active than the element you're kicking out in order to make the compound break apart and rejoin with you. So we have activity, what we call activity series, or this totem pole, if you will. We have one for metals if the A is the positive. Okay, so this is if you've got a positive ion. And we've got one for halogens. This would be if you're a negative ion. Okay. Or you can also flip in your packet to page 11. And in page 11, there's an activity series of elements. And again, this activity series here, this would be if you're a positive ion. And this column here is if you're a negative ion. Okay. And this is the list of activity. So if you are higher on this chart, then you've got more power. You can, if you're lithium, you can kick any of these other elements out of a compound. But if you're all the way down here in silver or platinum or gold, you're not kicking many people out. In fact, if you're gold, you're not kicking any of these people out. They're going to laugh you right out the door. You walk up and you say, hey, take a hike, man. I'm going to take your spot. They're going to say, yeah, good try, buddy. Good try. But if you're above them, you can kick them out, okay? Same concept over here, but this is just the list of halogens. And of course, who did you think was going to be at the top? Fluorine. It's the most electronegative element on the table. So it's got the most power. It's got the most ability to draw the other compound to it. Okay, so fluorine is going to be the king of the totem pole, so to speak. Fluorine can kick any of these other halogens out. poor iodine, though, can't do much, okay? So you follow the order when you look. So in this case, aluminum is trying to kick silver out. And if you look it up on the chart, aluminum is here and silver is way down here. So aluminum has the power to kick silver out. But if you were trying to write this in the reverse, silver couldn't kick aluminum out. Silver wouldn't be able to have a reaction, okay? And then in this case down here, fluorine is trying to kick chlorine out. And again, fluorine is above chlorine, so it can easily kick chlorine out and take its spot. And then this reaction happens. But I've put a couple examples in here for you. And so like here, lead, Pb, is going to be a positive charge, okay? And aluminum is the positive charge. So this is positive. Aluminum, remember we said, was a positive 3. And so lead is trying to kick aluminum out. So we look back to that chart. And aluminum's up here, but lead is way down here. So what happens is lead forms cations, but is less active than aluminum. So there's no reaction. So if someone tried to give you this to start, you would literally say, hey, no reaction. Ain't happening, buddy. Okay? And if you were bromine and you tried to kick chlorine out, because remember bromine, Br, is a negative, and chlorine, we know, is a negative. So bromine and chlorine, we'd look those two up, and we'd find that bromine is below chlorine. So again, no reaction. This is not happening, okay? But if you had someone like aluminum trying to kick lead out, right? Remember how we said these were aluminum and lead, Pb? Aluminum trying to kick lead out, well, aluminum is higher than lead, so it can happen. So aluminum, this happens, okay? This takes place. This is all things a go, okay? And then you can do the switch and figure out who your new products are, and then later you can balance them. And then in this case, if chlorine were trying to kick bromine out, because chlorine's negative and bromine's negative, and again, you go back to that chart, chlorine's above bromine, so this time it can happen, they can kick them out, okay? So when we're looking at the single replacement series, when we're looking at single replacements, you have to use your activity series. If someone's asking you to predict what the products are or if the reaction can happen, you go to the activity series and you say, okay, can this happen? Okay. And if you are above the element you're kicking out, you can make it happen. But if you're below the element, then it's a no-go. No-go. Okay. So again, not all single replacement reactions can actually happen. We use the activity series to determine if the single element is high enough on the chart to kick the other element out. If the single element is lower on the chart, the reaction will not take place. Okay. Now, if they just hand you a full-on reaction, and then they just might be asking you to identify it. But if they only hand you the front half of the reaction and they want you to figure out the back half, you got to decide, does it happen first before you can come up with the back half? Okay. Okay, here's your last one, double replacement. In a double replacement reaction, you've got two compounds. So it's two compounds trading spots and making two new compounds. Okay? And so it's just kind of like trading partners in a square dance. Like is going to replace like. We're back to that again. So when you get to A and B and C and D, when you get these compounds, pull out that red periodic table, flip over to the side of the ions, and start looking for charges. Remember that the front end of a compound should be positive, the back end is negative. The front end is positive, the back end is negative. So swap the two positives, okay? So A would come over here and bond with D. C would come over here and bond with B. And again, positive, negative, positive, negative. Okay? So if we were looking at this bottom reaction as your example, you've got HCl, okay, and H is a +1, Cl is a -1, and you've got MgOH2. Remember that Mg is a +2, OH is a polyatomic ion of -1. Then when you get to the other side, your positive is trading with the positive, and that positive is trading back. So now your H is going to be with OH, and your Mg2+ is going to be with your Cl negative. So here, when I go to make this compound, what does H and OH make? Can you spot it? It's H2O. And then what does this make? Well, crisscross applesauce, MgCl2. Okay, and so you can see where those formulas are coming from. Always using those charges. Okay. For the most part, we're just going to assume that all of our double replacements happen. We are not going to use an activity series with them for our purposes. But your new compounds are made using the ions charges. Look up those charges. Carry them over to the other side. Remember crisscross method. And all double replacement reactions are going to produce either water, a precipitate, or a gas. So they're either going to make water, they're going to make a precipitant that's going to fall to the bottom of the container, or they're going to create gases that are going to go blah, 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 and bubble right up the top. Okay, so you've got synthesis, decomposition, combustion. Remember we said this is going to be basically anytime anything burns. You've got single replacement, and if you need to know if it happens, you check your activity series. And then finally, double replacement, swapping partners. Okay, so if you go back to your packet and you flip back here to this front, you say, okay, hey, look, remember those lines Miss Lysick put in this packet on the right-hand side? And she labeled the right-hand side identifying chemical reactions. Well, let's take a look at number 1. What kind of reaction is this? If I look here and I'm trying to figure it out, I see one reactant. So I'm going to say that this is a decomposition. Okay? And my key is one reactant. I didn't put a T in there. A-N-T. Gosh, I can't spell for the beans. Okay, one reactant. Now I looked at number 2, and I see NaCl. Well, that's table salt. I know that. See AgNO3. Well, that's silver nitrate. Over here I see NaNO3. So that's sodium nitrate. And over here I see AgCl. That's silver chloride. So it looks like the Na and the Ag switch places. I see a compound and a compound, and I see 2 new compounds. So I'm going to know that this is a double replacement. And the key here is 2 compounds forming 2 new compounds. Okay? Okay, I know there is no number 3. That's going to drive me nuts. I'm going to have to fix that later. But here, H2 plus O2 yields H2O. Hopefully something is going off in your head right now telling you, I only see one product. One product. So ding, 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 I should know that this is a synthesis. Okay? I looked at number 5. I see NaOH. I see HCl. And on this side, I see NaCl and I see H2O. Remember, H2O is just another way of saying HOH, right? So this hydrogen came over here to where the sodium was and bonded with the OH. And this sodium came over here to where the chlorine was and bonded there. So I know this is a double replacement. Because again, 2 compounds forming 2 new compounds. I look down to number 6. I see polyatomics, right? I see those parentheses. And if I follow, aluminum left SO4 and went over to OH. So I see another double replacement. 2 compounds to 2 compounds. Okay? When I look in number 7, I see zinc and I see H2SO4, which is sulfuric acid. It's an oxyacid, right? Notice I don't say hydro because I got a polyatomic oxyanion here. So zinc shows up with SO4 on the other side, so that means it took hydrogen's place and it left hydrogen on their own. So I know that this is a single replacement because I've got one element, right, and one compound making an element. Oh, that's just ugly, isn't it? I'm going to have to erase that. Sorry, guys. I'm going to go with one element plus one compound is going to make one element and one compound. Okay, so that's a single replacement. I look at number 8. I see chlorine, and then I see sodium bromide, then I see sodium chloride, and then bromine all by itself. So that's another single replacement. So again, element, compound, making element, and compound. When I look down to number 9, I see zinc with copper sulfate, and then zinc sulfate and copper. So zinc took the place of the copper, so that's another single replacement. So again, element plus compound yields element plus compound. Okay, and then the last one that you see up here is going to be KClO3 breaking down to KCl and O2. So this is going to be a decomposition. And again, the key here that you're going to take away is that you have one reactant, and it's breaking down into simpler things. Okay, so this page we've now done. The only problem is we didn't see any combustion here. So if we flip over to, let's say, the third sheet, Roman numeral 3, we see CH4 plus O2 yields CO2 plus H2O. Here is a classic combustion because these items are always going to be the same. I know this is a combustion reaction. Okay? So when we look at a combustion reaction, again, remember that something is burning, a fuel. So this is my fuel, and it's burning in the presence of oxygen, and it's producing carbon dioxide and water. Okay? So this is what I'm looking for each time. Okay? Okay, so what I'd like for you to do now is I want you to go to page 6. I want you to move down the right-hand column, and I want you to identify 11 through 21 as either a synthesis, a decomposition, a single replacement, a double replacement, or a combustion. And I want you to flip over to identifying chemical equations, Roman numeral 2, which is page 7. I want you to move down the right-hand column, 1 through 9, and identify those. Flip over to page 8. Go down the right-hand side column and identify those. You can skip over 17, though, because there's nothing going to be clear-cut here on this one. I'll talk about it with you when I get back. Okay, so you're going to work on those. So your homework is going to be pages 6, 7, and 8. right-hand column identifying your equations, okay? If you need any other help, I will also post another video lesson up in your Schoology for this that you can go look at while you're sitting in class, assuming you've got some headphones. Okay, guys, have a great day. Talk to you soon.